So good afternoon. We're going to start with the Seminario Sandoval Vallarta from this week. This week we have our colleague Manfred Kraus, and Manny is asking for a renewal of his contract. Manny studied his PhD at Aachen University, and then he made a first postdoc at Berlin University in Humboldt University in Berlin, and then Florida University in Gainesville.
No, Florida State.
Florida State. Sorry about that. Yes. And then he came here in 2023, and he's going to tell us about part of his research because he has more topics. But today he's going to talk about the heavy weights in the particle world, which is the top-quark.
So, thank you for the introduction. So yes, so you have noticed I always alternate every year black holes and top-quarks. So this year we have top-quarks again. And the work I will be talking about actually started in 2016 during my own PhD. So and I think from that journey, you can see that science sometimes needs its time. So, and I will go through the main points of our results and our most recent paper here. Okay, so let's start a little bit about an introduction about the standard model of particle physics. So since 2012, we essentially have found the Higgs boson. And here, for instance, on the left-hand side, you can see the discovery plot where you have the data of the Atlas experiment. And you see this narrow resonance here, which is the Higgs boson. So it really fits the prediction really well. And since then, we have completed the standard model of particle physics. So now we have a bunch of particles. But in the end, everything that you're just seeing around you is just made out of up, down, and electrons. That's all the visible matter that we have. So then we have now more copies of things. So we have these charm top, strange bottom, muon, and tau, and they are just heavier copies of the electron up and down that we already know. But we don't really know why we have these heavier copies in the standard model. We also have neutrinos. They're still kind of a mystery today because we don't really know what is their nature really. They're Dirac or Majorana particles. And so this is still ongoing research here. We have then the photon that takes is the force carrier of electromagnetism. So this is also the reason why we actually have chemistry and lets you see this talk here. Furthermore, we also have then the strong forces is governed by the gluon, which actually makes up then binds to up and down quarks into protons and neutrons. And finally, we also have the weak force, which is governed by Z and W bosons, which facilitates radioactive decays. So this really is the process that's going on in the sun. And all of this is held together by the Higgs boson, which actually gives mass to all of these particles. So this is what we have experimentally established. And on the theory side, we can describe all of this in a quantum field theory with a local gauge symmetry, which is SU3 for the color degrees of freedom, SU2 for the weak interactions, and the U1 for the hypercharge. So before going into a little bit more detail, let's have a look what this quantum field theory actually looks like in a nutshell. And you can put this on a cup of coffee. And essentially what you have is here in the first row, you have kinetic terms for the force carriers, which tells you how also these forces interact with each other. In the second row, you have these Fermion terms, which not only tell you how matter propagates, but also how actually they interact with our gauge bosons. So then in the third row, we have the interaction of these matter particles with the Higgs field. And here we see that already that the Higgs field essentially couples to these matter particles proportional to their mass. In the kinetic term of the Higgs field, we also obtain Higgs gauge boson interactions, and also those are proportional to their masses. And finally, we have the Higgs potential, which tells us how the Higgs interacts with itself. So all of these things gives us the building rules of how we can actually compute in quantum field theory and do predictions for collider experiments. So really the key in all of this is how everything here works together with the Higgs field in the end. And the main problem that we actually had in constructing this quantum field theory is that the standard model symmetries require that all of the particles that we actually observe should be massless. But we know that electron has mass, W bosons have mass. So actually, how do you obtain a quantum field theory that is, but I have to think to follow it? No, doesn't want. So how do we obtain a quantum field theory that is consistent, but actually describes the real world that has masses? The solution to this problem is that you actually start out with this massless theory and then break the symmetry spontaneously, which gives rise to mass terms of your particles. For instance, in a nutshell, you have the Higgs field that lives in the Higgs potential, which is this typical Mexican head potential. And then typically we have that the minimum of this potential is not in the origin, but it's actually here in this valley. So we have a non-zero vacuum expectation value. So in the end, that means we have a phase transition that essentially goes from a Higgs field that has a mean value of 0 to something that is non-zero. Like a little bit simplified, essentially you now have to shift your field around this constant value and you just parameterize quantum fields around that non-zero point. So now every particle that actually interacts with the Higgs field obtains masses through this mechanism, because the only thing that you really needed to get masses to the gauge bosons is that you require gauge invariance. That means here this kinetic term is actually coupled by the covariant derivatives, and gauge invariance is all you need to get the prediction of the masses for W and Z bosons. However, the fermions are a little bit more tricky because there's no fundamental reasoning behind it why they should get the mass that they have. So essentially what you do is you write down gauge invariant interactions, but there's a lot of freedom of how you actually do this. And just by shifting this, you see that you end up generating something that looks like a mass term. So suddenly now, all the surprise, you put in what you wanted, you get out what you want. So why the fermion masses are actually like how they are still like a mystery. And on top, now we have actually short distance forces between all of these particles and the Higgs field. So we can actually study those things at a collider. So we also have now gone and measured all of these properties of the Higgs boson since we have discovered it. And for instance, here on the left-hand side, you will see cross-sections, measured cross-section for different production ways of the Higgs bosons, as well as different decay modes of it. And they're all normalized to the standard model prediction. And you see that as everything that is close to 1 essentially agrees with the standard model. And all of these measurements here are really compatible with our measurements and our theory. And on the other hand, we can also verify that these masses, that the coupling, the interaction of the Higgs boson to the particle is actually proportional to the mass. And we also see this here. And currently, for instance, for the top quark, we have this like at the 10% level established. And we even have now also the muon Yukawa coupling measured. So there's a lot of progress in these things. And we see that the Higgs boson actually looks very much like in the standard model. So, but there are actually like a few open questions. For instance, we don't really understand through this mechanism why there's a large hierarchy in the masses that we observe. Why are these just heavier copies of each other? And we also don't really know if there's now beyond the standard model physics, because so far everything looks very much like the standard model. On the other hand, if you now actually think about it, what you have actually experimentally measured from the Lagrangian of your theory is you have established the Higgs mass by a direct measurement. From these Yukawa couplings between the Higgs field and the fermions, we have essentially measured top, bottom, tau, and muon. And from the Higgs self-interactions, we only will be able to obtain limits even after the high luminosity LHC. So we don't really know if the Higgs potential really is the Mexican F potential that we assume, or if there are actually deviations from this. So in the standard model, these parameters lambda 3 and lambda 4 are equal. And what that means is that we have a very specific potential that we're living in. And experimentally explored, we only have here really like the minimum. If there's new physics and lambda 3 is not equal to lambda 4, this Higgs potential or this potential can look very different. And that means that there might be different minima. And we actually want to see if we can make conclusions about these things. So what I want to do is essentially, I want to study these kind of things, but through top-quark physics, because the top-quark has a very special role in the standard model. Namely, this is the heaviest of all of the fundamental particles. It's like 173 GeV, which is even heavier than the Higgs boson itself. So this is also very short-lived. So that means it actually decays before it hadronizes. So if you have like a W, that means that the spin information in the top quark is actually imprinted into the decay product of the W boson. That essentially allows you to study really like the spin information of this particle, and it makes it like the only bare quark that you can actually study. It also feels all of the forces, so it really interacts with all parts of the standard model, and it couples the strongest to the Higgs boson because this Yukawa coupling is essentially 1. So that means you can exchange Higgs bosons, 25 of those, and you will not have any suppression in your signal because all of this has the same strength. Also, because of its large mass, it actually facilitates all the rare meson decays. If the mass would be lighter or different, meson physics, flavor physics would look very differently. So just by studying the top quark itself, you really can do a lot of things. You can do electroweak precision measurements, you can study BSM connections, you can do precision physics, and you can also study flavor physics. The top quark is really like everywhere in particle physics. So what I'm interested in most for this talk is precision. And for instance, in the standard model, the masses of the W boson and the Z boson, they're not independent. If you now compute quantum corrections to the W boson mass, you will actually see that you get contributions that are proportional to the top quark mass, and also sensitivity to the Higgs boson mass through loop corrections. So now by independent measurements of the W mass, top mass, and Higgs mass, you can actually try to constrain or do consistency checks of these relations. And you see, for instance, here, you see the measurement of the W mass, the top mass, and here on the diagonal, you have different Higgs boson masses. And it's really like here's 125 GeV line, which is here in blue. That tells you that the standard model seems to be really consistent with the theory. So on the other hand, the top quark mass also has very important impact because it actually drives the quantum corrections to the shape of the Higgs potential in the standard model. So if you compute quantum corrections to this potential and you go to very high energies, you see that you're really dominated by the top quark. And what can happen is that depending now on the top quark mass value, either your potential stays stable or becomes metastable or even unstable. And current measurements really put us here at at the boundary of metastability to stability. So it's really like think like up to like 100 MeV make a difference in this study. So if the top quark mass is just slightly different, you will be shifted into like complete instability of the vacuum. So what I want to talk about today is essentially about how do we measure the top quark mass at the Large Hadron Collider. That is the rest of my talk. And so how do we do this in theory? So there has been proposed already in 2013 an alternative method of measuring the top quark mass. So you can do this, of course, from top quark pair production measurements of the cross section. You can do this from these electroweak precision fits. You can infer the top quark mass, but you can also use, for instance, TT bar plus 1 jet events. And the observable that one essentially does is you look at an observable that is essentially 1 over the invariant mass of the TT bar jet system. And you just plot this as a normalized distribution. And you see here is this distribution for different values of the top quark mass. So you see that you actually get nice sensitivity to the top quark mass itself. And so by measuring it, you could try to infer the top quark mass from this. So now you think, why do we do TT bar plus jet and not TT bar? TT bar seems easier. TT bar, we have better theoretical control over it. But if you see here on the right-hand side, this is essentially the sensitivity to of this process with respect to mass shifts. And you see here in blue, you see top quark pair production, and in green, you see TT bar jet. So on one hand side, we see that TT bar jet has a bigger sensitivity, so it is easier to extract the top quark mass using TT bar jet. On the other hand, for top pair production, this rho equals 1. Of course, you have a sensitivity, but you also get a new theoretical problem, because this is essentially the top quark pair production threshold. So here suddenly non-perturbative effects become important, like topomium bound systems and so on. Since we don't have very good control over these things on a theoretical level, making extractions here becomes very delicate. So that is the reason why we actually want to study TT bar plus 1 jet. So now the question is, do we actually have TT bar plus 1 jet under theoretical control enough that we can use our theory predictions to do these top quark mass extractions? And at the first, you want to generate TT bar jet, but in the real world, TT bar pairs will decay to W's and B's, and the W's will decay to leptons and all kinds of stuff. So the easiest signature that you could obtain is like a positron muon. You get 2 neutrinos, 2 B jets, and you get 1 additional jet. Now, from the experimental point of view, you have to think what other processes will generate the same final state. And on the one hand side, we have TT bar jet that has regular top decays. We also obtain TT bar processes that have now radiative top decays, where the hard jet comes out of the decay. We also get, so all of these are double resonant contribution. That means that they have 2 top quarks. We also get single resonant contribution from associated single top production. And we get processes that have absolutely no top quarks in there. So what a priori is not clear is if any of those other processes are actually relevant for the top quark mass extraction or not. If you want to do the calculation for this final state here, then gauge invariance actually requires you that you have to include the full 2 to 7 matrix elements if you want to include all of these processes. So we have done this calculation for 2 to 7. It's horrible next to leading order calculation. So just to give you an idea, like essentially like computing this for one single scale is like 1 million CPU hours that you have to burn. So, but we have been, so this is like 9 years ago. And we studied, for instance, at the beginning, just like total cross-section. Do we have any idea of how big are theoretical uncertainties on this? And for instance, we have here the total cross-section as for different scale choices. One is like a fixed scale, which is just the top-quark mass, and then we have dynamical scales. One is where we essentially reconstruct what is this intermediate top-quark momentum, and one is like very agnostic, just like take the PT of everything that's in final state. And you see that for the fixed scale, you get like 35% uncertainties. And that goes down up to like 10% if you take this agnostic, process agnostic scale. So this is really like, so we chose in the end HT half because this gives us the smallest uncertainties. And you see also that the cross sections are really like compatible with each other, even within these uncertainties. So if you now also go to the differential level, and you just plot here the differential cross-section as the function of the transitive momentum of the B-jet. Then you see here in blue leading order and red next to leading order results. And the band here is this variation or independent variation of these scales. So this is the envelope of all kinds of 7 different calculations. So what you see is that NLO corrections can be large. They can be like up to like 55%. But here actually we have a problem because here in the tail, the NLO cross-section turns negative. So that already means that something is not correct. So the reason for this is essentially that in these dimensionful observables, you can directly pinpoint where the production threshold is. Namely, the scale of the top-quark mass is very good once you just can barely produce a TT bar pair. So that's like here at the beginning. But once you're going really like to high energies, then the top-quark mass should not be the correct scale anymore, because now you have like a TV of energy out there. So what you want to do is you want to use a dynamical scale that somehow depends on the PT of your final state. Because essentially in the high energy limit, you have that the top mass will be way smaller than any PT. And that means the alpha S of PT will be smaller. That drives actually these corrections to be smaller in the tail. So and if you compare this, here it's just the same observable transitive momentum of the B-jets, but just for different scales. And suddenly you see an improvement on the convergence of your perturbative calculation. So while you still have like very big 10% corrections here, uncertainties, but now all of these next to leading order calculations actually overlap with the leading order one. So while also what's interesting actually is that it's mainly that the leading order prediction shifts, because that one obviously is very sensitive to the choice of alpha S. The next to leading, like at least the central prediction does not shift severely in most observables, but you see that it really improves also the estimates of the uncertainties. So now you can do this also for other observables, like the PT of the hardest jet. And here you essentially see the same conclusions, that once you go to these dynamical scales, actually the predictions become very stable and very, very good. You really have like residual of like 10% theoretical uncertainties, even at the differential level, like up to like 400 GeV here. But you also see that these NLO corrections are not like completely constant. So you actually have to include these things here correctly. Things look a little bit different if you go to angular observables. So here, essentially, if you go from fixed scale to dynamical scales, you don't really see like a big change in the conversions of the theory. You see that the corrections overall shift a bit, but that's about it. So the reason for this is an angular observable receives, like in an angular observable, you cannot typically pinpoint to a specific bin of where you just have the production threshold. So even at production threshold, you will fill out the entire observable range. That means even for these angular observables, even the fixed scale is a good one because you are very inclusive. In these dimensionful observables, it's typically only like the first few bins where the fixed scale actually makes sense. Beyond that, you need to go dynamical. You can also address uncertainties through atom distribution functions that parameterize the content of the proton. We also studied this, and essentially with like 3 different PDF sets, you see that you get up to like 5% uncertainties, in even at like very high energies, but they are definitely smaller than any scale uncertainties that you still have. So on the PDF uncertainties, you don't really have to care for now, unless you go to like next to leading order and things. Of course, will not happen anytime soon. So we have kind of an idea that we can do these calculations, and then they are actually very accurate. Now the question is, do we actually need this heavy calculation, or can we use something more simple to do the top-quark mass extraction? So in the end, what we want to do is we want to compare things. So we have our full offset calculation that is like really like 2 to 7. These are like tens of thousands of diagrams that you have to compute. Or we can compute the same observable using the narrow width approximation. In the narrow width approximation, you will restrict the intermediate top quarks to beyond shell. And essentially, you get contributions from TT bar jet, but also from top quark pair production, where you have these radiative top decays. And then you can also, what we call narrow width approximation production, is that you have the jet only in the production part, and you only compute next to leading order QCD correction to the production part, but you take leading order decays. This is typically what you can do with most event generators in the if you try to include pattern shells and so on. So we have 3 different predictions, and we can now see how the differences actually impact the accuracy of the top quark mass measurements. At the first observation, if you just compare like total cross section, you see that you get 2% differences. And this is consistent with our expectation that the differences should be somewhere of the order of the top quark width divided by its mass. So, but now the question is this also 1-2% at the differential level? So now we're going back to that observable that we wanted to compute to do the top quark mass extraction. And we see here our this observable now in the full offset calculation and these 2 narrow width approximations. So here in the upper, we just see the NLO corrections, but the interesting one is here the difference of the narrow width approximation to the full offset calculation in percentage. So first of all, in blue, you have the narrow width approximation, which fluctuates a little bit around the here in this region, but then in the high energy tail, you see some kind of difference, which is expected. But overall, you get like a very good approximation of this observable. But if you actually drop these contributions that come from TT bar production and single top production, so you have only the TT bar jet in the production, you see here in green that you really get huge corrections, nearly like 100%. And the reason is, of course, around 0.8, that's where TT bar jet production dies out. Like we have a minimum PT cut, So you need an energy of something like 2 times the top mass plus the energy of that PT of the jet to even produce that final state. So in green, simply there's no phase space left for you to produce TT bar jet events. In blue, you have TT bar production essentially filling out that region. And in the off-shell calculation, you also have single top production, all this continuum production that fills out this region. And these differences are actually important because, as you see here, this is really the region where you're sensitive to the top quark mass. So what typically means this translates to is if you only have on-shell TT bar jet, you have a very strong sensitivity of the top quark mass, but it's not a true sensitivity because all these other processes will wash this out in practice. So we have now done like a little experiment. We took our theoretical predictions and we did like our toy experiment. We took our best prediction for the full offset calculation and generate pseudodata according to this distribution. And we take all of our other prediction as templates for different masses and different PDFs, different scales. And you just try to use these templates to fit your pseudodata. And from this, you can extract the top quark mass simply by chi-square fit. So then we repeat this like 1,000 times with 1,000 different pseudodatas. And in the end, you get like a distribution of your extracted top quark mass. And from here, you can extract what is the mean and what is the stretch. And we did this. On the one hand side, we assumed that we have an integrated luminosity of 2.5 femtobars. And essentially, so these are all nice numbers, but so what this number here is always our cross-check because it's the same theoretical prediction that we use to generate the pseudodata. So if that one does not give you what you want, then you know that you did mess up something. So we see like minimum mass shifts between input and output of like 180 MeV. And in general, what you see is that for all of these predictions, fitting that observable is essentially very well. However, we see that depending on the theory, it really seems like you get like really strong shifts in the mass. So like if you're using the narrow width approximation to extract the top quark mass, you end up like either way too big or way too small. So in principle, you can correct for this. But of course, the best thing is that there's nothing that you need to correct. There are less uncertainties connected to these corrections. So we now try to look at what happens if you have tenfold that data, 25 inverse femtobarn. And now the picture changes quite a bit because the statistical uncertainty goes down on your measure, on your extractions. So you get like very precise statistical uncertainties. But essentially, you can now at the theory level distinguish all kinds of theory input. It's the narrow width approximation is really like between like 2 and 5 sigma excluded. But you even are sensitive to the choice of scale. For instance, here in the full offset calculation, but just with a fixed scale, you also get a 3 sigma deviation from your input then. So that's something that tells you that this measurement is first of all very sensitive to this non-resonant contribution. It's sensitive to the top quark decays. It's sensitive to the scale choice. And if you actually try to do a scale variation on top of this, you'll see that you get like something like a GeV uncertainty that you can at best get out of here. So given all of that, the idea is now actually how do we use, we clearly see that you need this kind of prediction to do this top quark mass extraction like very accurately. So that's now essentially how the theory meets the real world. And since this year, there's a measurement of the Atlas collaboration of the top quark mass from TT bar plus 1 jet production. And for that paper, I made it on the paper. So it's finally my first experimental paper. So they now measured this distribution and they unfolded back to either TT bar on share plus jet. So that's what they have been doing in the past. But they also unfolded back to our calculation, which takes into account essentially TT bar jet, and single top reduction. And you see on the one hand side, from the gray band here is the theoretical uncertainty. And you see that this full offshore calculation here is a bit more precise than the onshore prediction. But on the other hand, you see that here in the beginning, the onshore calculation is definitely more mass sensitive than our 2 to 7 calculation. That is, we already knew that before, because here, this is where all the other processes like single top production actually kick in and wash out your sensitivity a bit. So now they try to extract the top quark mass from both of these calculations and see, they can see a difference from that, essentially. So what you also have to take into account is now exactly the same. You have to simulate if you know the top quark mass, like how much does these things actually shift? Like how much of a shift in the top quark mass do you expect? And the shifts are rather small. They're like 200-300 MeVs. But it's very interesting that actually the dependence on the top quark mass is very different for these calculations. I don't have like a good explanation why this is, but this is definitely something we need to understand better in the future. In the end, we see here, this is really the measurement of the top quark mass. We get something like 171 GeV, and we have like all of these with statistical uncertainties, systematic, scale uncertainties, and PDF uncertainties. It's very interesting to see now that even though we had that the theoretical predictions here were more precise in our 2 to 7 calculation, in the end, they turn into a larger scale uncertainty on the top quark mass. And to my mind, this is simply because the onshore calculation underestimates the uncertainty a bit. Okay, I think I'm very quick today. So comparison to other. So we have our top mass here is now 171 plus 1.5 GeV. So compared to all the other differential equation, all the other top quark mass measurements, we can either have like inclusive TT bar production or also previous measurement of TT bar jet. And we see that we are very compatible from using kinematical observables to extract the top quark mass. I think the puzzle remains why electroweak precision fits tend to be a little bit higher. For that, I don't really have a good understanding why this is happening. But this essentially already allows me to conclude now. So I was happy to contribute to the very first top quark mass measurement using a full offshore calculation that includes all of these decays and non-resonant contributions. We actually figured out that the single top contribution and non-resonant contribution are really important in this game. And as I mentioned before, it is really like remains to get a better understanding of these scale uncertainties here, because it seems to be, to me, a little bit counterintuitive. And of course, there are still remaining uncertainties in this that can be essentially eliminated. For instance, none of these calculations are directly there where the measurement is done. Like the measurement is done at the level of hadronic final states. So in order for them to compare to our calculation, what they have to do is they have to combine all of these hadrons again and essentially undo the shower evolution to get to a final state that only has 2 B jets, 2 electron muon, and so on. In the case of the onshore calculation of the 2 to 3 calculation, they have to go even further back. Of course, this unfolding back to this front shell, to the intermediate 2 to 3 or 2 to 7 final states, is dependent on Monte Carlo simulations, which at the moment are all 2 to 3 with parton showers. And there's some kind of uncertainty related to that. One could eliminate that in the future by interfacing these 2 to 7 calculation actually with parton showers. And then you really can do the measurement, the top quark mass extraction at the level of the measurement where it's done. Then there you have eliminated most of the theoretical unfolding procedure. Okay, that's already all I wanted to say today. Thank you.
We have plenty of time for questions, so otherwise he starts asking. So does anybody have an understanding why electroweak precision measurements is off to a right?
Why that is off? I don't know, to be honest. I think typically they are loop suppressed, these top mass correction, because it's like the W mass measurement then, where you get the top quark through the quantum correction. So they might be just less sensitive to this, and that's, but why they're pushed to higher mass. We think that really boils down to lab data in the end.
Okay.
Lab. Before my time.
Yeah. And if the W mass changes, how does that affect your calculation? Because remember, there was a shift on the W and then it came back. No, I know, but it doesn't really affect. So
if it would shift by 2 or 3 GeV, that we will see. But if it's like a few MeV, no, this is the thing. Nothing will happen to this.
At the beginning, you mentioned the importance of these results of the stability of this potential. What else can you say now? Was really not interesting.
For that, we can't say at the moment, not because so these TT bar jet measurements, they are not yet at the level of the precision that we need. And TT bar jet typically suffers from larger uncertainties than TT bar, even though in this selection here, it doesn't seem to be the case. But typically, TT bar jet has higher uncertainties on the top quark mass. So for instance, at some point, it will also get important if it's all mass, if it's MS bar mass, all of these renormal ambiguities. Like the second you get this thing here below a GeV, it becomes theoretically like a nightmare.
So what would be this will be included in the PVG?
I hope.
Okay, so what would be the average? What you were showing first, 173 point something?
The average.
You
yeah, the
173
is like the PDG number.
PVG. So they will push it down a little bit or something.
Probably a little bit, but as the uncertainties are not diluting it too much.
Yeah. More questions? Now's your turn. 10 minutes. Okay.
The grouping of the C-quark with the Higgs is not in the plot, I think, in the presentation.
No, do we actually have a measurement?
No, that's why I'm asking. I mean, why not? Where is not a measurement of that topic?
Probably you really have to distinguish jump jets. I think that is the nightmare. You have to somehow see if there's a light jet, if it's a bottom jet or a jump jet. Like my naive expectation would be that this is a horrible question to ask. Like to the data. These uncertainties are just too big to make at the moment any claim on the charm coupling. They are definitely their constraints, but let's see, there typically is. I think this plot is from last year. So Not sure if there's something with chunk quark in here. Yeah.
More questions or comments for Manny? Well, if not, we thank him again. Very nice. Very impressive.